All right, and we are back for the second part of this video lecture on Chapter 3, Section 3. Remember, we were discussing what the derivative can do for us, right? Like what is, we've spent all Chapter 2 learning these recipes, these techniques to take a derivative. And now we're asking the question, well, what can this do for us? So we just got done seeing that the derivative obviously has a way of being able to tell us when a function is increasing or decreasing, right? But now we're actually going to find another application for the derivative. And this is the idea of the first derivative test. So before I read this any long-winded math definition to you, can I just give you the intuitive guide of what this first derivative test is saying? Will you agree with me if you're walking, right? You are walking, I don't know, you're just going for a stroll. If you go from walking downhill to then walking uphill, do you agree with me that there must have been a point where there was a minimum, right? There must have been a point where you are at your lowest ascent, in other words. Likewise, if you're out for a stroll and you're walking uphill, and then at some point, we'll call it C, you then begin to start walking downhill. Don't you agree with me that there was a maximum, right? What we call a relative maxima somewhere in that stroll, right? You can't go from going uphill to going downhill without reaching a maximum point. Now, that is actually what the first derivative says, that look, if you find some value C, if all the x values to the left of C have a negative slope, and all the x values to the right of C have a positive slope, that means your slope went from negative to positive. That would mean you can't go from negative to positive without crossing zero. And when a slope is zero, we're going to find our relative minimums and maximums. All right. So at this stage of the game, I think that just little brief intuition guide to the first derivative test will suffice, right? But the formal way of, again, mathematicians are very careful in their wording. So the formal way of defining all that I just said was, okay, that the value of C would be a critical number, and we'd have to require some things, right, from our function. We'd have to require that our function is continuous on some open interval. Now, continuous means you should be able to draw it without ever lifting your marker, without ever lifting your pencil. And we require that critical number be somewhere in that interval. The other things that we require is that the function has to be differentiable on the interval. Okay, now, except possibly at the critical number. It doesn't have to be differentiable at the C value, but you have to be able to take the derivative. It has to be differentiable throughout the entirety of the function. But if we meet these conditions, then we get to make a statement about f of c. We get to say that f of c has a relative minimum if your slope changes from negative to positive. We get to say that f of c has a relative maxima if your slope changes from positive to negative at the point C. All right, no more theory. We'll jump into a problem. I want to give you one definition that you may hear me say either, somewhere in a preceding lecture, and I want to make sure that I give you that definition before I go any farther. So if you ever hear me say a strictly monotonic function, a strictly monotonic function means that it's either always increasing or always decreasing, right? It's everywhere increasing or everywhere decreasing. All right, now let us jump into an example. So, ready? The question asks for us to find the relative extrema for the function 1/2 x minus sine of x in the interval 0 to 2 pi. Okay, so remember, we'll go through these. I'll go through these as quick as I can. So remember, the first step in this process is going to be to take the derivative. All right, how about we make a statement? When in doubt in a calculus class, take a derivative. How's that? So the derivative of 1/2 x minus sine of x is simply 1/2 minus cosine of x. Okay, so step 1 is done. Now step 2. Step 2 is to find the critical numbers, right? So we want to find where f prime of x is either equal to 0 or f prime of x does not exist. Okay. So let's start with the latter, right? Does not exist. So if you know your trigonometry, you would know that cosine of x is defined throughout its entire domain. In other words, cosine of x is never going to be not defined. You're never going to have to worry about the division by 0 or the square root of a negative number. None of these are going to apply. So there's no critical numbers that are going to exist when f prime of x does not exist. So let's now look at what about if you have f prime of x equal to 0. Okay, so the goal is, let's go ahead and rewrite the derivative. So f prime of x is equal to 1/2 minus cosine of x. And what are we going to do? Well, we're going to set the derivative equal to 0. And you're going to solve for x. So maybe you're thinking, how do I solve for x? It's a trigonometric function. Well, let's do it. And maybe it's been a little bit since you've done some trigonometry. So the way we're going to do this is let's first isolate the cosine. Ready? So let's subtract 1/2 from both sides. So now I have negative 1/2 is equal to negative cosine of x. All right, well, no need to have negatives on both sides of the equation. Let's get rid of them. Let's divide by -1, divide by -1. So now I have 1/2 is equal to cosine of x. Remember what I said? The first step is to isolate the trig function. And now the question that you're asking yourself is what x values, right? In other words, what angles, what radian angles will, when placed into cosine, will give a value of 1/2. All right, now how do you do that? Well, you have to look at your unit circle, or you'll have to, maybe you have placed certain parts of that unit circle to memory. Either way, we're going to have to somehow reach the fact that that is true when x is at pi over 3 and when x is 5 pi over 3. With me? Because we are done with step 2. We have found the critical numbers at pi over 3 and at 5 pi over 3. That derivative equals 0. So where did we go from here? Remember, now we're at step 3. So step 3 is where you start to set up that table, right? And remember, I used the words. I said, let those critical numbers subdivide your number line. So, okay. So I've drawn a number line, negative infinity to positive infinity. I've just placed a 0 on the number line, and now I need to take the pi over 3 and the 5 pi over 3. Okay, ready? So let's place them in order. We read the numbers left to right on our number line. So pi over 3, and then 5 pi over 3. All right. So that zero is not part of the critical numbers. I was just there to help you label the graph. That's all. No need to even place it if that is at all confusing to you. Now, what do we have? Well, again, imagine you have a long string and you make 2 cuts. Right? If you have a string and you make 2 cuts, how many pieces of string do you have? You have 3 pieces. And likewise, you have 3 intervals. So what are the intervals? Well, we have an interval from negative infinity all the way to pi over 3. And we have an interval from pi over 3 to 5 pi over 3. And then the last interval is 5 pi over 3 to infinity. All right, so that's the intervals. And now what do? We're going to approach it the same way we did example 1. We're going to need a test point. Okay? So it's your job to pick any number from negative infinity to pi over 3. I would just suggest you pick a number that's easy to work with, right? But it doesn't matter. It's up to you. I'm going to pick pi over 4. And then I need a number from pi over 3 to 5 pi over 3. I'm going to pick pi. And I need a number from 5 pi over 3 to, well, I said infinity. I should actually restate that. If you look at the question, it doesn't say to go to infinity, does it? It does say to go from 0 to 2 pi. So no problem. No problem at all. That's an easy fix. So let's go ahead and pick some angle that's from 5 pi over 3 to 2 pi. I can pick any angle that I want in there. I'm going to pick something easy to work with. How about 7 pi over 4? Okay, so at this stage, what do you do? Well, we take our test points and we plug them in to our derivative. Right? So we're taking pi over 4 and we're plugging it in to the derivative. Same thing with pi. Same thing with 7 pi over 4. Now, I need you to understand something really quickly, because I don't really care, and you shouldn't really care what f prime of pi over 4, the numerical value that it's equal to. The only thing you and I care about is it going to be a negative number or a positive number? Okay, because if it's a negative number, we're going to say that it's decreasing. And if it's a positive number, we're going to say that it's increasing. And that's really it. That's all that we care about. So you can grab your calculator, right? You don't need to have an exact value, because we only need the sign. So if you plug in pi over 4, just make sure your calculator's in radians. If you plug that into your derivative, what do you get? You should get out a negative number. And if you plug pi into your derivative, you should get out a positive number. And finally, if you plug in 7 pi over 4 into your derivative, again, you're going to see a negative number. Okay, beautiful. So now let's make a statement. Negative slopes, that tells us that we are decreasing. Positive slopes tell us that we are increasing. And last, negative slopes tell us that we are decreasing. Okay, so will you agree with me that as you were walking from 0 to pi over 3, throughout the entirety of that walk, you were decreasing. You were walking downhill the whole time, right? You see what I'm talking about here? You are decreasing. So, okay, but as soon as you got to pi over 3, what happened? Well, you then started to walk uphill. You started to increase. So you went from decreasing to increasing. So how are you going to go from decreasing to increasing? Right? Without what? Without having a minimum value, a relative minimum somewhere in there. Likewise, so you were walking uphill, you were increasing the whole way, all the way till you got to, so I chose 7 pi over 4, all the way till you got to 5 pi over 3, I mean. And then what happened? Well, as soon as you got to 5 pi over 3, you start to walk downhill, you start to decrease. So you went from what? You went from increasing to decreasing. And so in that case, there must have been a maximum somewhere there. All right, now let's not be sloppy. Let's actually, the question that was asked of us, the task that we had was find the maximum or minimum. Find the relative extrema. So let's finish this problem. Ready? So we get to say that at pi over 3, right? So when x is pi over 3, we have a relative minima. We have a minimum. And we get to make the statement when x is 5 pi over 3, we have a what? We have a maximum. So remember, there's a subtle difference in it's hard to even spot. It's so subtle, but there's a difference. There's a subtle difference in asking what is the relative minima or where is the relative minima, right? There's a difference between me asking you what was the most money you've ever made in your life, or at what age were you making the most money you ever made in your life, right? So asking the question, where is the relative minima, is really asking the x values. Asking the question of what is the relative minima is really a question of the y value, okay? So there's a minimum at the point pi over 3 something. I don't have that, I don't have a calculator readily available. So if you plug pi over 3 in for your original function, you would find your whatever y value that is. And there's also a maximum when x is 5 pi over 3. And again, I don't have a calculator, but if you were to plug that into your original function, you would find that maximum. Okay, so where do we go from here? Well, for the most part, the theory, the techniques are, I've taught you. You have, in other words, you have what you need to be able to do any of this work that would show up on a quiz or a test. Nothing's going to change. Now, what I'm going to do is I'm going to do an application of this first derivative test, so I can show you how it's, at least the usefulness in something outside of just textbook mathematics. But it should go without saying that all you really need at this point is just some practice, right? You just crack open your book, find some examples, and go through the same process that I've went through for the last 2 problems. All right, so let me jump into an application. Are you ready? So, okay. So now forgive me if my healthcare providers out there, any of my students out there who have studied anatomy or physiology or biology, I may goof up some of the on the science here, but I can definitely do the mathematics. So let me read. So a trachea. So we're gonna discuss the contraction of a trachea. Ready? So let me read. So it says coughing, right? So coughing forces the trachea, the windpipe, to contract. Now, this affects the velocity of the air passing through the trachea. So in this case, they say the velocity, V, of the air during a cough is modeled as follows. Ready? So we have little v. That doesn't look like a little v, does it? That looks like a big V. Let me try that again. Little v is equal to K multiplied by big R. Hold on, we'll come back to that. Minus little r multiplied by little r squared. Okay, now let's see if we can make sense of this notation. So in this case, what is the v? Well, the v is the velocity of what? Of a cough. All right, and what is little r and what is big R? Let's start with big R. Now, so as I was saying, so the obviously when you cough, the trachea contracts, right? So the you could think of the radius of your windpipe contracts during a cough, right? Big R is going to be the normal radius of the trachea. Right, so the normal radius of the trachea, whereas little r is going to be the radius of the trachea during the cough. All right, and what is this K? Well, this K is some constant. Now, again, I have no idea. This is not my area of expertise. I would assume that the K is probably because everyone is going to have a different size trachea, and that K is what's going to represent, say, your trachea versus mine. Ready? Now, so we have the function that models the velocity of a cough. And we're told that r, little r, the radius of your trachea when you're coughing, is always going to be somewhere between 0 and big R. That makes sense to me, because at most you could contract all the way to 0. That would be like if you were choking. Well, maybe not choking, but if you were to contract all the way to 0, you would have 0 radius. You would have 0 air leaving your lungs. But it doesn't have to contract all that way, but it has, in order to say that it contracts, it would have to be less than the normal radius of your trachea. Okay, so what do they want from us? It asks the following question. What radius will produce the maximum air velocity? Now, I have no idea why you are interested in this, in the question of coughing at the maximum velocity that you possibly could cough at. But that's okay, because the mathematics can help answer this question. We're going to figure out at what radius would you produce the maximum velocity of a cough. Ready? Let's proceed. So how do we do this? Well, remember step one? Step one is always to take the derivative. So let me go ahead and write. So V is equal to constant K multiplied by big R minus little r multiplied by r squared. Now, I'm going to make this derivative a little bit easier I'm going to go ahead and distribute the r squared. Right? I have not taken the derivative yet, So v is still going to be k, and now it's going to be multiplied by big R times r squared minus, well, r times r squared is r cubed. All right, and now this is a much easier derivative to take. So what do we want? We have v, that we want v prime. All right, so remember that you are taking the derivative of v with respect to, well, you have little r, big R, k. What are you taking the derivative with respect to? Well, you're taking the derivative of v with respect to little r, with respect to the radius of your trachea during a cough. So let's go ahead and take that, that derivative. So the k is a constant that's going to remain there, and the derivative of big R times little r squared is going to be 2r times little r. And the derivative of r cubed is going to be 3r squared. Okay, now, bear with me. I know there's someone watching this video thinking, wait a minute, why isn't my professor using implicit differentiation? Well, because, look, k is a constant. That's not a variable. Big R is a constant. That's not a variable, right? I mean, I don't know what the radius of your trachea is, but whatever it is, it's constant, right? The only thing that changes is the radius when you're coughing, right? It's the little r is the only variable in this equation. So step one is done. We have a derivative. I'm going to make life a little bit easier on myself because I'm going to factor out an r, but what is step two? Step two is to find the critical numbers. Ready? So we're going to set v prime equal to 0. So I'll do this. I won't do multiple steps all at once. I will refrain from doing so. So let's set that derivative equal to 0. And ready, let's make life easy on us by factoring out a little r. So this is going to be k multiplied by little r. And what's left in here? So this would be 2 times big R minus 3 times little r. All right. Now, so that is where the derivative equals 0. We're going to assume that you and I exist, so that our tracheas exist, so we won't worry about finding out where the derivative does not exist. So now let's answer the question. So what R values would make your derivative equal 0? So this is, of course, when R is equal to 0. And now follow me over here. Let's go ahead and figure out the second R value. All right. So now many of you can you can do that in your head, but I'm gonna come off to the side and write 2 times big R minus 3 times little r. I'm going to set that equal to 0, and I'm going to solve for r. So that would be negative 3r is equal to negative 2. Let me go ahead and give myself a little bit of space here. So this would be negative 3 times little r is equal to negative 2 times big R. Let's get rid of those negative numbers on both sides of the equation by dividing by negative 1. So that leaves me with positive 3 times little r is equal to positive 2 times big R. I'm almost there. Got to divide both sides by 3. And there we have it. So what is r equal to? R is equal to 2 twice big R divided by 3. Okay, now what is this actually telling us, right? Maybe you're thinking, Professor, you didn't even give me any numbers to plug in. No, I did not. But all I'm going to do right now is try to explain what the math has told us. What the math is telling us is that when the radius of your trachea is 2/3 the normal radius, you will have reached the maximum velocity of a cough, right? So just keep that in mind next time you're coughing. Just decide to, try to restrict your trachea, contract your trachea to 2/3 what it normally is, and there you'll have the maximum velocity of a cough. Okay, I will see you again soon.